All right, so I'm Janelle Klein from New Iron. So we're a software niche recruiting company in Austin. And today I wanted to talk to you guys about one of the biggest challenges in software development, how to break the software rewrite cycle. So whether it's been my project or someone I was working or consulting with, the story's kind of been the same from every project. So it goes kind of like this. So we start out with the best of intentions. We're going to write high quality code with low technical debt. It's easy to maintain, and of course it's got to have good code coverage. And things start off okay, but our problems are invisible, and they're hard to explain, hard to communicate to our management. And these problems start building up over time, and we talk to our product owner about our concerns, and they're like, we've got more important things to do. And so we keep deferring the problems. And then as the problems build, our releases start getting painful and chaotic. And we're down to the wire and the software's broken. And we're staying up late nights and weekends trying to fix bugs and push last minute changes in production. And I mean, everything turns into these last minute exciting releases. And instead of our management seeing all this chaos as evidence of the problem, we're congratulated for the all-nighters and our great teamwork. They keep up that great work ethic. Then we get into the thrashing stage, where essentially we're spending more time fixing our problems and dealing with all the pain than we are making progress. And our environments are going down, and the builds are breaking, and nothing gets done without pain. And our management now is just in a panic because productivity's slowed to a crawl. And they're like, we need to go faster, so let's hire more developers. So now we've got developers breaking things because they don't even know the software. And it's a full-time job just to keep the software from falling apart. And eventually exhaustion sets in. And that's the tipping point for project meltdown. There's usually one last-ditch effort by the team to turn things around. But if management says no and the team loses hope, it's the final nail in the coffin, and the developers start leaving in droves. I give up. I don't care anymore if the project fails. And that's when project meltdown starts. So the further down the path we are of escalating risk, the more tempting it is to hit the right reset button. So if you think about it, we can be free of all the baggage of past mistakes. All we got to do is hit that reset button. But with invisible problems and business pressure that doesn't let up, we just keep repeating the same cycle, the software rewrite cycle. So this talk is going to be about how to solve this problem. So if you've ever felt this pressure on your project of business pressure that doesn't let up, and all these problems building that you can't get time to work on, and despite your best efforts, you end up with unmaintainable software anyway, that's what I'm going to help you solve today. So what's wrong with our current strategy? I mean, we talk endlessly in our industry about how to make software more maintainable. And I was reading this book, Good Strategy, Bad Strategy, and I found my answer by the first chapter. It says, a description of the goal is not a strategy. So if you look here at our strategy for success, it's pretty much a description of the goal. And we talk a lot about in our industry about what maintainable code is and why it's important. But what we don't talk about is how the hell we're supposed to pull this off in the context of a business system. The problem is we don't really have a strategy for solving this problem, and we really need one. So Rumelt says, a good strategy is a specific and coherent response to an approach for overcoming the obstacles to progress. So what are the obstacles that cause the software rewrite cycle? And what specific approach are we going to take to overcome those obstacles? So about 8 years ago, I was on this project, and we were trying to do all the right things. And I was in the same boat. We had CI, unit testing, design reviews, code reviews, all the things you're supposed to do. But still, my project ended up hitting a pretty good-sized brick wall. And we brought down production 3 times in a row, and then spent the next 3 years rewriting the software. So in trying to help my project, I started digging around in the data, and I thought the main obstacle was technical debt that was building up in the code base and causing us to make mistakes. And that if we made changes to code that had more technical debt, we'd be more likely to make mistakes. So I wrote this tool that could detect these high-risk changes, and I thought, hey, well, if I can detect the changes, then I'll be able to know where we need more testing so we can prevent these problems. But what I found in the data wasn't what I expected at all. Most of our mistakes were in the most well-written parts of the code. And you did read that correctly. Like our senior developers that wrote the best code in the system, that's where most of our bugs actually were. And so that kind of puzzled me a bit, but I did find one correlation. We made significantly more mistakes in the code that we didn't write ourselves. So it seemed like our mistakes were more associated with lower familiarity than the code quality itself. And while that made some sense, it seemed like there had to be more to the story. I mean, this is what I knew. When I had to work with complex code, it was really painful. But what made development actually feel painful? So I started keeping track of all my painful interaction with the code and visualizing it on a timeline like this. So the pain started when I ran into some unexpected behavior, and as a result, when I found the cause of that behavior. So that was 5 hours and 18 minutes of troubleshooting. I think most people would agree that's pretty painful. So the amount of pain was driven by two factors: the likeliness of that unexpected behavior and the cost to troubleshoot and repair the problems. So if I wanted to understand what was causing the pain, I needed to understand the things that were causing these two factors. And so every time I ran into an example problem, I started classifying these things into categories. And one of the first things I noticed was a lot of the causes of the pain weren't things that were related to problems in the code. They were more related to human factors. For example, stale memory mistakes. Right here. Hey, I can use the highlighter. All right. The stale memory mistakes are essentially when you have a memory of how something works, but it doesn't work that way anymore. Some other developer changed it, but you're relying on that old assumption. Or ambiguous clues. This is when the code has, the behavior you see has two possible ways it could be occurring, and you make a bad assumption about what's causing the problem, and kind of down the rabbit hole you go in troubleshooting. Both of these things are ways that humans can get thrown off track and make troubleshooting take a long time, but they aren't necessarily related to technical debt. But once I understood what was causing these kind of problems, most of these problems were actually fairly easy to avoid. So let me give you an example of an avoidable problem. So a common case is, we write a little code, we iteratively validate the code with unit tests, and when you do this, it's usually pretty fast to troubleshoot the problems. But if we're in a hurry, we might go, well, I'll skip the unit tests and worry about that later. And then we end up spending all day troubleshooting problems. So when we're in a big hurry, it's really easy to make what I consider high-risk decisions, in that if I make no mistakes, skipping the unit test does really save time. I can usually save a couple of hours. But if I make lots of mistakes, I can end up in troubleshooting hell and lose 8 hours of time for the whole day. So when we're in a big hurry, we don't tend to weigh these risks appropriately, because troubleshooting time just goes by really fast. When you're kind of in that zone working, the time just zooms on by, and we don't make very good trade-off decisions. So our software is a reflection of our decision-making habits. So our decisions are ultimately the root cause of our pain. So if we're in the habit of making high-risk decisions, these problems with unmaintainable software is what we get as a result. And so if we rewrite the software and start over, but don't fundamentally change the way we make decisions, our problems just keep coming back. And this is how we get in that rewrite cycle. We think that we can get rid of our problems by getting rid of our code, but technical debt is just a symptom of the problem. So technical debt has us focused on code quality and looking for problems in the code, as opposed to looking for these problems in our decision habits. So I want to give you a new metaphor to think about. mopping the floor. So I want you to think about how much work does it take to mop the floor in relation to how much work does it take to complete a software task. So I was in a big hurry mopping the floor, mopping as fast as I could. And then my dog Tango, he comes trotting across the floor making muddy footprints. And I was thinking, well, I could go and put Tango away, but now he's just laying there on the carpet watching me. And I thought, he'll probably just stay there. So I mopped up the muddy footprints. And I bet you can guess what happens next. So Tango comes walking across the floor again. And by this point, he was pretty amused by this little game and made all kinds of footprints all over my floor and left me tons of work to do. So how do we relate this back to software development? How much work does it take to complete a software task? So Tango represents the risk, the likeliness of an event, and the potential impact. The muddy footprints represent the side effects from ignoring the risk. And we make trade-off decisions between a direct cost, like writing unit tests, or an indirect cost, like troubleshooting mistakes. And we tend to make high-risk decisions because these indirect costs, like troubleshooting time, are so hard to quantify. So in software development, these side effects come in 3 flavors: troubleshooting, learning, and rework. And each side effect is a function of risk. So troubleshooting risk we've already talked about. It's driven by the likelihood of unexpected behavior and the cost to troubleshoot and repair the problem. Learning risk is driven by the likelihood of working with unfamiliar code and the cost to learn those things. So this would be things like having lots of third-party libraries, if you have lots of turnover on your team, a really huge code base. All of these things affect how much time you have to spend learning. Rework risk is the likelihood of making a bad assumption and the cost to correct the decisions. So this would be things like making a bad assumption about the design or solution, making a bad assumption about the requirements. And the longer we delay before making a correction, generally the higher the cost is of correction and repair. So all 3 of these functions are risk correlated as opposed to something that's static in the code. There's a chance that something can go wrong and a chance that we'll have to deal with recovering from those problems. So if we go back to our stages of escalating project risk, there's a vicious cycle fueling this process. So first we ignore the risk and basically ignore Tango. A lot of times the risk isn't really all that obvious. So it's not necessarily a deliberate decision that we're choosing to take a shortcut like technical debt would suggest. Sometimes we just don't realize we're taking a risk when we're taking one. And then the risks increase and our Tangos basically multiply and that risk impact keeps increasing. And then as we're doing the work, there's way more side effects and stuff that we have to deal with and more mopping work we do from all the frequent bugs and higher task effort. So then as we get further behind on deliverables from all this extra work, the time pressure continues to build, and that's when we get this horrible feeling in development of managers screaming at us because we can't go any faster, and we're like, I can't go any faster, and yeah. Anyway, but productivity plummets because of all the overwhelming side effects. So if we look at what this looks like in those visualizations I've been showing you, I'll show you a few case studies on different projects. So this one is from a healthy project about 10 months old where we were actively working on trying to reduce troubleshooting time. So even with just normal everyday problem solving, about 10 to 20% of our time was still spent on friction. The second case study is from a project about 18 months old, and these guys are working on a rewrite effort of a huge platform, and essentially they're under a lot of pressure to hit feature parity before they can get this thing out the door. And so under all that pressure, within 18 months, they're already spending about 40 to 60% of their time troubleshooting problems. And nobody's doing anything about it because it's so hard to see still from the outside. They're just like, why aren't things going faster? And they're in that boat of trying to hire more developers because development isn't going fast enough. So this last case study is what I consider a post-meltdown project because all the original developers on the team left. And you can see what happens. Essentially, you start spending most of your time figuring out what to do and like 10% of your time actually doing stuff. one of the things you'll notice by comparing all three of these things is that all of the tasks on these are like 1 to 3 days still. So even as the problems grow and get a lot more complicated to deal with, we're generally still able to break down the work into bite-sized pieces. The effect of that means that we can't see these effects by measuring velocity or task lead time. They just don't show up. What we do within those time periods drastically changes, though, as we shift from more doing to more thinking time involved in the tasks. All right, so what specific approach are we going to take to overcome these obstacles? So this is where the Idea Flow learning framework comes in. And Idea Flow is a metaphor for the human interaction in software development. So you can think of ideas flowing between the developer and the software, and friction is everything that gets in the way of that flow. So this Idea Flow map, is these visualizations I've been showing you, are essentially highlighting that friction in Idea Flow. So the learning framework is a strategy for improving software predictability by optimizing developer experience. So most people are like, well, what does that mean? So it's essentially a way to drive down troubleshooting, learning, and rework by systematically identifying and mitigating the risks. So essentially, we're going to find the risks, find the tangos, and put them on a leash. All right, so the first obstacle is developers typically aren't given time to work on improvements because nobody understands these problems that are going on. So developers are stuck because they don't have control, but management is also stuck because they don't have visibility into the problem. So we're actually in a state of organizational deadlock here. So everybody's basically waiting for a resource they don't have. So if we want things to change, we have to be willing to step outside the bounds of our role, because otherwise everybody's just stuck. So if you want things to change in your project, here's what you need to do. First, make the decision to lead. So step 1, don't ask for permission. So leadership is not a title bestowed upon you. It's a choice to take responsibility. Sorry, I'm kind of like reading the notes. I'm like, pink is troubleshooting, yes. So the pinkish red color, that's the troubleshooting. And I'll try and keep legends on all the slides so you guys can see them. But anyway, don't ask for permission. And Nike has a pretty good slogan here with just do it. I mean, you need to take the first step to make something happen. Step 2 is make the goal clear to your team. So here's what you can say. I want to make the business case to management for fixing things around here. No more chaos and working on weekends. This needs to stop. But I need data to make the case, so I need everyone's help. Step 3, state the plan. Here's what I'm thinking. I want to run an experiment to record data for 1 month on all the time we spend troubleshooting. We can look at the data together and identify our biggest problems. Then I'll write it up and present the case to management to get things fixed. Step 4, enlist the team. Will you guys help me make this happen? So focus on getting your team on board first and get everyone collecting data. And then the next step, you'll need to make the case to management that change is a safer decision than staying the course. So the key to success with this is to focus on the risks, not estimating how long things will take. So if you just kind of try and paint a picture in terms of things costing more money, then management thinks that they can just throw more money at it and solve the problem. But the reality is that you can't really solve problems with escalating risk by working harder. You have to work smarter to get out of the problem. So you need to convince your management that the project is more likely to fail if you stay on the current path, and that the indirect costs are more expensive than mitigating the risk. And finally, after you scare the crap out of your management by showing them all these examples of data, then you need to take responsibility. And specifically, ask for a 3-month trial with dedicated resources, control of all decisions for improvement work, and then make a commitment to show results in 3 months. So generally speaking, by fear tactic and then taking responsibility, I've never seen this strategy fail. But if you have trouble with this or you need some help, feel free to send me an email. I'm happy to give you some advice. So after you get time to work on improvements, the next challenge is getting results. So the idea flow learning framework has 3 steps. Make the problems visible, understand the problems, and then improve decision habits. And I've got a sort of mini sub-framework for all the steps in each one of these. So first, we'll look at making the problems visible. So first is the reflection framework, and the goal is that visibility helps us to identify the problem. So there's 3 steps. Clarify the strategy, record what happens, and ask questions. So first is clarify the strategy. So to do this, I draw a solution strategy diagram, and it has 2 parts. There's conceptual model of what your intended solution is. So these are just kind of like the conceptual chunks of how you're thinking about the design and what you're planning to do and the dependencies between them. And the second part is the path from A to B, basically a list of subtasks, but it specifically encapsulates your strategy of if you're going to do vertical slices or how you're going to break down an approach that works. So the idea is that once you do this, it's a lot easier to talk through the strategy with a peer and look for potential risks and then reflect on the strategy when we finish. So that's the first step. So second is recording an idea flow map. So I used to do this process on pen and paper, but that got pretty cumbersome. And so I wrote this tool. It's an open source IDE plugin that looks kind of like this. So you can set your active task that you're working on, and then there's 3 buttons for troubleshooting, learning, and rework. And then the output of the tool is these visualizations I've been showing you. So these event markers, I keep track of the subtasks as I'm working with events, and then when I look back on the task, I can kind of see what happened in each particular area of the task. And here you can see I have a legend and troubleshooting is pink. All right. And if you zoom into the details, you can see all the files that you were working on, how long you're working on them, and you can see things like, let's see here, yellow is probably not the best color, but you can see I'm kind of bouncing back and forth between tests and the actual code. So you can see when someone's actually doing unit testing, or here, down below, where it's bouncing between coding and deactivating. Generally speaking, somebody's firing up the application and testing it that way. So as opposed to just looking at the output of code that somebody produces, you can see their technique and how they're approaching problems. So in next up, you can click the individual bands of time and kind of zoom into the details. So in this case, I can see there's a problem here of why isn't the token showing up in the URL? And there was a typo here that they found in the email template, and that took 1 hour and 8 minutes on. So after we have an idea flow map, the next step is asking questions. And this is where things get a little more interesting because you can learn to read the visual indicators in idea flow. So similar to how an EKG helps doctors diagnose heart problems, and these little blips on the EKG map back to particular activity in different parts of the heart, idea flow maps help developers diagnose software problems. So the heart of software development is essentially problem solving. So similar to how from an EKG we can see different parts of the heart, in an idea flow map we can see activity in different parts of the problem solving process. So the problem solving process I modeled kind of like this. So first, we have this stage of evaluating alternatives. Basically, we kind of look around at the different options and come up with a general strategy for what we're going to do. And then the modeling stage, we scan through the code and try and build a conceptual model of how it works and how the different pieces are going to fit together. And then we go into this feedback loop process where we write a little code, validate that it works, and keep iteratively refining our strategy. And sometimes we run into a problem where our strategy isn't going to work, and I call this a strategy conflict. And essentially you go back to the drawing board and you're evaluating alternatives again. So this is what the problem-solving process looks like for software development. And when there's disruptions in different parts of this problem-solving process, we see a different effect in idea flow. So I'll show you examples of each piece of this. So when there's problems with evaluating alternatives, we see this kind of tumble pattern of trial and error, the red, blue, yellow striping. So the red is the strategy conflict that we run into. Our plan ain't going to work. And then the blue is going back to the drawing board. We have to learn and figure out a new strategy. And then the yellow is the rework, where we have to implement our plan B. And when you're in trial and error over and over again, you see this pattern repeat, red, blue, yellow, red, blue, yellow. So if I saw this pattern, I would ask, well, how did you evaluate the options and choose a strategy? What was wrong with the different strategies you tried? What was the discovery that made you choose a different direction? There's problems with modeling. I get a whole lot of learning time, and these red bands are strategy conflicts where there was some unexpected dependency that threw a wrench into my plans before I even started coding. So in this case, I would ask, were you working with something that you were unfamiliar with? Did you run into code that was noisy, ambiguous, or misleading? And what do you think made the code difficult to learn? When there's problems with refining, we have learning time that ends up being part of those tight validation circles late in the process. And you get this distinctive striping pattern where you get kind of blue, white, red, white, blue, white, red, white. And that usually is an indicator of struggling with complex details. So if I saw this, I'd ask questions like, did your task involve changes to complex code or business rules? Were there lots of details that you had to keep in your head? What was causing the complexity in the validation cycle? And if there's problems with the validation cycle, we're struggling to get feedback on something. So you can think kind of running experiments and not being able to get the feedback that you need to figure out what's going on. So I'd ask questions like, what experiments did you run to troubleshoot the problem? How many times did you run the experiment? How long did it take you to get through each experiment cycle? These are all things that drive up the duration of those red bands. So problems with execution, you can see a noticeable increase in the frequency of mistakes. So this happens when the changes are especially mistake prone. So I find this effect a lot when I'm working in JavaScript. So I saw these, I would ask questions like, was there something in the code that made these changes especially mistake prone? How familiar were you with the language and tools you were working with? Were you tired or distracted when you did the work? All these things can increase the frequency of mistakes. So the point of all this with asking questions is so we can identify problems with our original strategy. So the strategy diagram that I showed you before, that kind of gives us a picture of what it is we're planning to do, and then when we see the output of the results, we can ask questions as to whether that was a good plan and start identifying those problems. Yeah, this picture probably would have helped. Anyway, okay, so the strategy diagram's here. So we get feedback and loop in the process. All right, so that's the first step, the reflection framework. So step 2 is understanding the problems. So typically when we start off an improvement effort, we start by brainstorming a list of possible improvements. And we think of things that bugged us recently, how we're not following best practices, and then there's like that code that just makes us feel shameful that we just got to fix. And we take all these items and we stick them into our technical debt backlog, and then we start chipping away on our improvements for a few months. But what usually happens is these problems that come to mind usually aren't the right problems to solve. And so we have an effect kind of like this, where the improvements we work on aren't our biggest problems, and then our improvement effort doesn't end up making that much difference. And so even though we're spending months on working on improvements, nothing's really improving all that much. So don't do this. Brainstorming is a pretty ineffective way to come up with an improvement list, I found. Things come to our mind for a lot of different reasons other than it's the biggest problem to solve. So instead, I'm proposing a modeling framework that basically a way to systematically go about figuring out what your biggest problems are. So the process is driven by this focus meeting, where as opposed to focusing on everything, we're going to focus on one thing at a time. And the focus meeting will drive through this 4-step process: finding the biggest problem, modeling the causes of the problem, running experiments to test our understanding, and then clarifying our decision principles. So first step is finding the biggest problem. So this is the most involved. So the basic idea is to categorize the problems by type And then we want to focus on the problem with the highest friction. That's the basic idea. And then all of these bands of time, in order to categorize them by problems, I'm putting hashtag problem tags on the idea flow maps themselves. So the more challenging part is what problem categories do we use? And as I started categorizing these problems, I noticed they all started culminating around the same kinds of categories. So I started calling these the 10 pains of software development. And I was looking at these for what are the different problems that affect this problem-solving cycle. So we'll go through these. Design fit pain is when the new feature doesn't fit well into the design. Requirements pain, bad assumptions about what functionality to build. Collaboration pain, challenges collaborating with other developers on the team. Modeling pain, when it's difficult to build a conceptual model of the existing software. Cognitive pain, challenges with complexity and intense thinking. Alarm pain, challenges with false alarms and test maintenance. Experiment pain, challenges with getting feedback by running experiments. And execution pain, when changing the code is highly mistake prone. And then we've got lack of familiarity and disruption pain, which are a little bit different than the others because they have more of an amplifying effect on other problems. They're not so much affecting the task, but our capability to do the task. So if I categorize all the problems by these different pain types, I end up with a chart that looks kind of like this. So you can see over here with the ones that are more on the left side of the problem solving, you get more yellow and blue, and on the right side you get more red. So you can see here that experiment pain is my biggest problem category. So the nice thing about categorizing things by how they affect the problem solving process, whereas most things where we make an improvement, you can't really see the effects. Well, with this, if you make focused improvements on experiment pain, for example, you can get a visible effect in terms of reducing troubleshooting time. So you get really nice correlations to get visible objective feedback as to whether your improvements are actually working or not, which we've never been able to have in software development before. So the second part of finding your biggest problems is finding areas with high resistance to change. And this is a little bit different than how we're used to thinking too, because we're used to kind of looking statically at our code and trying to find problems. It's not really how these problems work. So we have our starting state of software, and we have the ending state that we're trying to get to, and all the stuff that gets in our way is friction. And it happens in the context of movement. It's not something that's static in the code at all. So friction is always relative to the movement of the system. And if there is no movement, there is no friction. If you aren't changing the code, there's nothing that's getting in your way. Different areas of code will move in different ways. So if we want to understand the causes of friction, we need to understand how our system moves and changes over time. And the kinds of bugs that get introduced and the kinds of problems that we'll run into are always relative to the kinds of change that we're making. So if I aggregate the data by these areas of functional areas of code, you can see effects kind of like this. So this is sort of the 100% bar of how much friction there is and which percentage in different functional areas. So you can see from here that the reporting engine has some kind of problem going on. We're spending about 80% of our time there working on friction. So if I was just looking at this from a static state, I might think, okay, well, this is a really important problem to solve. But in reality, if I looked at this friction versus upcoming demand, you can see here that the reporting engine isn't going to be moving at all. We're not developing any new features in it. In fact, we're developing a lot of features in the JavaScript UI, and which still has a substantial amount of friction. It's probably a higher area of friction to worry about. So the other thing to keep in mind is even though we're looking at correlations with the code, that doesn't necessarily mean our problems are in the code. So if you look at friction grouped by familiar versus unfamiliar developers here, you can see a lot of our problems are caused in the context of developers that are unfamiliar with the JavaScript UI, and the familiar developers don't seem to have many problems at all. So this is another common thing to happen when you have a really high learning curve in a particular area and you've got a lot of knowledge siloing going on. There might not be anything wrong with the code, but you can reduce friction dramatically just by spending some time pairing, for example. And these knowledge management kind of things are another thing that kind of goes off to the wayside a lot of times. But if we've got a lot of upcoming demand in a particular area and all of the knowledge is siloed in one place, you've actually got a pretty good sized ticking time bomb on your hands. So one thing to warn you about here. When you're aggregating data like this, you got to be really careful in not doing comparative before and after type analysis. So I'm using this to figure out priorities, but when you're comparing things for 2 time periods on 2 different task sets, it's really easy to say, oh, we improved, look at how much better this is. But in reality, the tasks can be so wildly different that friction will be wildly different just because the tasks are different, and there's nothing here but statistical variation. It doesn't necessarily mean you improved. So don't do this. Instead, when I mentioned this before, we want to focus on the biggest problem-solving pain. So if you want visible indicators that show you improved, this gives you that comparison. And it's not perfect, but we can basically compare examples of the same pain type between tasks. So because problem-solving is just problem-solving, an experiment is just an experiment. And when we're conceptually trying to figure out something in our head, or we're collaborating with peers, there's a lot of similarity, even though the task can be wildly different. So if we focus on reducing the biggest problem-solving pain, we get that visible feedback to help us know if we improved. So this is when you walk away with this first step of finding the biggest problem, you want to know what your biggest problem-solving pain is, number 1. All right, so next up is modeling the causes of the problem. So let's say we chose experiment pain, and now we want to know, well, what's causing experiment pain? So in this case, I've tagged this particular example with experiment pain, and then I'm going to ask questions. Well, why did it take an hour to find a typo here? So I'm going to ask the question, and then, well, I ran experiments by firing up the application and sending email. That was a slow feedback loop. And the problem was tricky to track down. I sent 23 different emails, so that was numerous feedback loops. So these problem categories here are basically causes of pain. So I started building a table of these and then trying to categorize each example I found into these different categories. And once the category is stabilized, I'd go and dig one level deeper and look at all those examples, and each time I'd try and categorize a problem. If there was an existing category, I'd put it in that category. If not, I'd make a new one. And I kept repeating that process until I filled out a tree that looks kind of like this. So these are all the different causes I have of experiment pain. And as I identify which problem categories are most prominent that I'm running into the most often, I can direct my attention towards the biggest cause of the problem. All right, so that's how you model the causes of the problem. So next up is running experiments. So running experiments sounds like this big, complex process, but it's really actually quite simple. We run ad hoc experiments in the context of our development that look kind of like this. There's 3 steps. So 1, make a decision. 2, predict the effects and IDEO. And then 3, see if you get the results you were expecting and ask why. So I'll show you an example. So as I'm working, I might say, I'm going to run final testing by firing up the app. I've written good unit tests along the way, so I predict that troubleshooting will be quick. The troubleshooting took 4 hours. Why? Another example. I'm going to skip writing unit tests and run the report manually. Since it's a slow feedback loop, I predict that troubleshooting will take a long time. And all troubleshooting took 2 minutes or less. Why? So we've been, with best practices, we tend to think that unit tests are good and skipping our unit tests is bad, but it's not really that simple. And that these details and nuances and exceptions that come out of running experiments help us to understand what really causes pain and the dynamics of that are pretty complex in software development that drive these factors. So the experiments help us correct bad assumptions about what really is a better decision. And it usually isn't until we get conflicting data like this that we start changing the way we think about software development. So the final step is clarifying decision principles. So what does better really mean? This is kind of a nebulous term in software, but we talk about it a lot. And better tends to mean better following best practices. But what we really need it to mean is better solving the problems. So in order to do that, though, we really need a fundamental shift in our industry from best practices that are solution-focused to decision principles that are problem-focused. So what's a decision principle? So a decision principle answers two questions. How do we evaluate our situation? And what are we trying to optimize for? So let me give you an example. We start off with a kind of nebulous comment, kind of like this. You know that thing that happens when you make too many changes at once and it's really hard to troubleshoot problems? Well, we want to avoid that. There's a lot of wisdom in this phrase, but it's not all that clear what we're trying to say. And we don't even have words to describe these things that we experience every day that we try and optimize for. So the first step is giving those things a name. So I'm going to call this the haystack effect. The number of unvalidated changes has a huge impact on the difficulty of tracking down a problem. So we want to minimize the size of the haystack. So then we can ask questions like, if I decide to skip the unit test, how will that affect my haystack size? Another example that's a little more complex. You know when you run an experiment it's really hard to figure out what's going on? Well, we want to avoid that too. So with that one, I use the code sandwich metaphor. So experiments are a lot more than running the test. We have to set up the inputs, then run the test, and interpret the outputs. And the difficulty of diagnosing the behavior is driven by the difficulty of manipulation, the complexity of the behavior, and the difficulty of observing what's happening. So the code sandwich, by reducing the thickness of my code sandwich, I can reduce the diagnostic difficulty. So with this metaphor, then I can ask questions like, how can I design my code sandwich to make this problem easier to troubleshoot? It's a lot easier to say. All right, so that's what decision principles are. And the modeling framework helps you find your biggest problems and then figure out what are the things that you need to do to start making improvements. And the last step, so the goal of understanding the problems is to identify the critical few things that will make the biggest difference. So this is essentially Pareto's law, the 80-20 rule. So now, finally, last step, improving decision habits. So we talked about that the high-risk decisions are the root cause of our problems. And this is all well and good, but how do we actually go about changing our decision habits? Well, we stop and think. And I ran into this a while ago when I was trying to coach another developer on testability. And I was trying to, review their code and give them feedback, but it didn't seem to matter what I did. They kept repeating the same kinds of bad decisions. So I was like, okay, I need to pair with them and help them out that way. I need to change how they think. And so I started practicing asking them the right questions at the right time, essentially Socratic method. So I'd wait till just the right moment, and then I'd poke the developer right when they were struggling with an experiment. And then I'd ask them questions. What aspects of the behavior are you trying to observe? What aspects of the behavior are you trying to manipulate? How can you reduce the thickness of your code sandwich? So one of the things I learned about testability is really just designing for experimentation. And so if I wanted to help them understand how to write more testable code, I had to teach them how to think about experiments. So this eventually became the stop and think framework, which is essentially training wheels for improving decision habits. So I left the developer with a piece of paper that had my questions on it. And for a while, I'd spend some time poking them, but I'd basically give them that list to take home manually and practice with. And at first, I'd use explicit checklists, and then once they, got the habit down, I'd take the checklist away, and they'd basically do it on their own. But as you finish a task and you're kind of looking at what happened and trying to figure out how to improve, instead of just going, oh yeah, we should not do that in the future, instead more systematically you think, what questions could I ask my future self to recognize this problem in the future? And then you come up with what questions you can ask in what situations, and then use those as explicit checklists to help you drive decision improvement. And that's the stop and think framework. So the goal of improving decision habits is to make the improvements permanent. So that's the idea flow learning framework. Make the problems visible, understand the problems, then improve decision habits. So then instead of the software rewrite cycle, we can break the cycle and work our way to software happiness. And also, if you did like the talk, please help me get the word out. I should have my book done this summer, and I'm giving away free ebooks to anybody that's interested, since nobody knows what I'm talking about right now. It's all kind of a new foreign language, so all the help I can get in getting the word out would be a big help. And all you got to do if you want a free ebook is just send me an email. And my email is janelle@newiron.com. You can find me on Twitter at JanelleKZ. So does anybody have any questions?
Hello, thank you, Janelle. This is Pedro. We are receiving some questions through the chat. I'll approve them so that they show up in the chat. A recurring theme from some of the audience was about personal software process and team software process. And in Mexico, it's a popular popular thing. I don't know how to call it, a method or a process or a model, but yeah, Software Engineering Institute's TSP and PSP are popular in Mexico. I don't know if you can comment on if you looked into that, or how does it relate to what you're doing with Idea Flow?
Sure. It's probably one of the things that's most similar to what I'm doing. PSP is really not popular around here at all. Most people haven't heard of it at all, so it's kind of interesting to hear that feedback. Its difference with respect to what I'm doing is that it's focused on optimizing for human interaction factors. So it gives you visibility of fuzzy things like what it takes to understand things, and looking at patterns over, how your system changes over time and how mistakes actually occur from a human interaction perspective. Like we have these ideas about how modular code is supposed to make code more maintainable. And well, sometimes when you go and try and make the code more modular, it doesn't make it more maintainable at all, and it ends up causing other problems. For example, another developer that's familiar with how the code used to work now has to relearn this new way of working, and may end up making mistakes just because they aren't familiar with it. And if we're constantly kind of moving things around and having to relearn them, that doesn't necessarily make things better. It can solve problems, but there's a lot of trade-offs that once you start looking at what's actually going on, it can be quite error-prone. Another common thing I see is when it comes to test maintenance. And we write all kinds of tests, and testing is considered really good, and a lot of times testing can be extremely brittle. And if you pay attention to how your code changes over time, and then design your tests around how your system changes to detect bugs, I tended to find that I started actually deleting a lot of my unit tests I was writing because they weren't all that useful from a bug protection standpoint. They'd help me initially with control, but unit tests I found tend to actually be pretty crappy regression tools. Yet it's very much standard in the industry to have high code coverage. So there's a lot of things that I've fundamentally changed my beliefs and principles about what is good coding practice, but it's built around really understanding your problems in your team and the brains on your team and things that are going on an intimate level. And instead of focusing on following best practices, focus on understanding your problems really well with your team.
Another question that was made, that was earlier, people asked if you could, how can they build these maps themselves? You mentioned the tool or a plugin that you made for an IDE, I believe.
So the tool is available right now on ideaflow.org. It's a little bit, since I'm still in, the only people using it right now are like me and my team pretty much, and a few folks that I've been consulting with. So I'll have a release that's a little more functional out when I release my book. But I mean, there's a version available. It does work. It's a little clunky, but it's functional. You can collect data if you want to, but it's open source. It's only supported on IntelliJ right now. But I'm planning on getting a tool that's outside of the IDE, as well as porting the tools to a bunch of different environments. And I'm planning on building a analytics product that can help with, like all the aggregating and stuff that I'm doing here in this presentation. I'm doing this with a spreadsheet, and it's kind of painful. So one of the things I'm wanting to do is build some really good analytic tools for this. But I'm planning on productizing that, but all of the base tooling will stay free.
Great. Does anybody else have any other question for Janelle? We have a couple of minutes left. Let me see. Recuerden, I'm just going to make the mention of your book in Spanish in case some people didn't catch it, Janelle. Recuerden que Janelle en este verano va a sacar un libro con mucho de lo que mostró aquí. Va a ser un libro electrónico gratuito. Si les interesa obtenerlo, mándele un correo a Janelle ahí en su email que está poniendo ahí. También síganla en Twitter, en Janelle KZ. Ahí ya también puso su dirección de Twitter. Okay, Janelle, looks like that's it. It was, I mean, the concepts were pretty clear. Looks like you're doing something very interesting. Thanks so much for your participation, and we'll keep in touch, okay?